And filtrated. So.
Yeah, thank you. You know, I'm very happy to be here, and I was here maybe I was here last month in yeah, well, I think in early maybe end of November, and we were having lunch together, and then you know, Sean invited me to this conference, and I was, you know, very excited to come back here in January, and I said yes, I will come, and then I went back home, and then I started thinking, okay, what I'm going to talk about actually at this conference. I mean, so I wasn't really sure whether, you know, I would have something interesting to say that would fit in the theme of the conference. But that was too late. I was already too late. So I was here yesterday, and it was really nice. I was, you know, wearing shorts in January. That was really great. The talk is this idea of iterative filtering that I want to sort of present. It is essentially the problem of trying to get maximal likelihood estimate when you have a state space model. A lot of work has been done on that, but I want to specifically talk about the case where you have a signal dynamics where the distribution actually of the signal is intractable, and for this kind of, it's actually a very, very difficult problem when the signal is intractable, and some of the ideas, some of the old ideas that are sort of well known kind of break down, and we have this idea of iterative filtering that I thought it would be nice to talk about in front of this audience. So this is a slide just to present a discrete space model. I will not use it much, but I think it's, I guess, it might sort of set the notation a little bit. So X will be the signal, and it's unobserved, and Y will be the observations related to the signal this way, just the usual state space model. And the goal here is that, of course, we have a copy of the observations, and we would like to use it to estimate the parameter theta, which is a p-dimensional parameter. And I'm particularly interested in the case where the signal density, transitional density is actually intractable. There are a lot of problems where this actually arises, where you cannot actually compute that. And we have this very simple and nice idea, which doesn't require this transitional density. Everything is just based on the ability of sampling from the signal. If you can simulate the process, then you could actually use it to use sort of simulation to estimate the parameter. And it's an interesting way of using, actually, as I will explain later, it's an interesting way of using Bayesian method to actually do frequencies computation. Just to write down a little bit more formally, so this would be my likelihood function. And of course, it's obtained by integrating out the unobserved signal. And what I want is to get to approximate the maximal likelihood estimate of the parameter. A classical example is this one, where you have a diffusion process, and that you're interested in. People in finance deal a lot with this particular problem, where you have a diffusion process, but you actually observe it only at some fixed time, T1, T2, Tn. But in most, and of course, the goal here is to estimate the parameter that's driving the process. In most cases where of interest, the transition density that you get, so of course this is you know, you could use the Markov property to say that you know, to go from T1 to ST2, but these transition density actually are intractable most of the time. There are a lot of actually work that have been done. One of the simplest things that people do is to say, well, okay, let's just think of these the observed path as the discretization of the SDE. But you know, it's obviously, if the observation mesh is not tight enough, that will actually introduce a lot of bias into it. And there are a number of ways, much more sophisticated ways, to try to do something more closer to approximating the to stay close to the continuous time diffusion that have been pushed recently in these works. But of course, the computational cost actually increases quite heavily. So the method that I will present today is it could be used to deal with this problem. But more generally, of course, there is also a lot of other applications where we have really real state space, where you know, you have the signal, but the observation are also sitting on top of the observation process is also sitting on top of it, and the signal process is a diffusion, and it has intractable transition density. And one area where this you have this kind of issue is in epidemiology, and where for example, you want to study a particular disease, and try to understand how the disease is spread, and the virulence of the strength of the infection, things like that. And one way that people often use to do this is, of course, complementary models, where they will split the population is infected, susceptible, and recovered. And you could actually write down SDE for this. You know, it's classical thing that they do, where they write these. They look at these proportions and write SDE for that sort of capture very well the dynamics of the population. But then of course they're interested in the parameters in this SDE. But of course, these are very, very difficult to you know, if you have a large population, being able to follow everybody and know their status is a very complicated thing. But what they can get oftentimes would be perhaps the number of infected over a certain period of time, the number of deaths perhaps over a certain period of time, and this gives you a very natural state space model that fits in the description that I gave earlier. And the question is, you know, whether we can estimate the parameters given the intractability of the transition densities. So here is a slide that sort of explains a little bit some of the ways that one could proceed. One way is to say that, well, we could take this and do importance sampling, right? Then sampling from this density Q, and then reweight and get something like this, and then maximize this. But this actually, in the applications that I mentioned earlier, just completely bogus. It won't work. Just won't work. You could maybe do a little bit better by doing SMC, by doing sequential Monte Carlo instead of importance sampling. You could improve that a little bit if you do sequential Monte Carlo. But it turns out that if you do sequential Monte Carlo, you get, the approximation is no longer smooth actually because of the resampling. If you do resampling as part of the sequential Monte Carlo, you get something that is no longer smooth as a function of the parameter, and it becomes very difficult to maximize. And also, computationally, it also makes sense. It also seems to be that perhaps it's better to try to solve this instead of work on the likelihood scale, which can introduce some other numerical issues. So in practice, it's actually better to try to find the to set the derivative to 0 instead of tackling directly the likelihood function itself. And of course, you could do that, and looking at the derivative, if I take this is my likelihood function, looking at the derivative of the log of it, you could write it, my Fisher's identity, you could write it this way. And in this particular case, because of the structure that I'm giving to this joint here, of course I can write it this way. And at that point, we could bring in stochastic approximation, because now, in order for me to approximate this gradient, all I need is actually just to sample from, essentially do filtering, to sample from the unobserved signal given the given the observations, and the particular value of the parameter that I'm looking at to try to approximate the gradient. So you could do that and get, excuse me, get approximate gradient and use that to do stochastic approximation the same way you could do EM. It turns out that you could also do some sort of a stochastic approximation driven by SMC, by sequential Monte Carlo, in the sense that this is just, here you could also just get estimate of this distribution by SMC. And that gives you another way of doing stochastic approximation. But all these methods actually, as you could see here, they all require that we get the gradient of the log density of the transition log transition densities. And so in the diffusion example that I mentioned earlier, you cannot, because you don't have access to these transition densities. So the talk is just to sort of introduce this idea of iterative filtering. It's a very simple idea, and I'll mention some convergence results, but overall, it's just present the ideas. I will not sort of go into too much of the technical details. And in fact, I think we still haven't sort of you know, done all the analysis to say all the things that can be said about the method, and so I'll have a lot of open questions that through the presentation. Some literature. I should say that the main idea actually is due to my colleague Ed Arnides, who came up with this idea of iterative filtering in this paper, 2006 paper. PNAS paper. But the justification that they gave when they wrote the paper was actually not right. But they used the method to solve some really interesting, do some really interesting science that study cholera, dynamics of cholera, and it was actually a very interesting paper that look at large-scale cholera dynamics and the effect of people that shows very little symptoms when they contract the disease, and the role that these kind of people play in transmitting the disease at a large scale. And we got together later on to try to sort of understand really why it works, and we did something on it in 2011. And in this paper, we tried to sort of connect this idea of iterative filtering to Bayesian computation, and sort of intersection between Bayesian computation and optimization. And that's mostly what this talk will be about. And there are still a lot of, as I mentioned, a lot of open questions that I'm still trying to sort of understand. All right. So to focus on the idea, I'm just going to consider the very, very simple case. A very simple case. I have some likelihood function L, and it will be the exact same one that I presented earlier. But here I'm just going to consider a very simple problem where I have a log likelihood function L, and I'm just trying to for a given value of the parameter, I want to calculate the gradient of L. Ultimately, I want to find the maximum likelihood, the maximizer of the function. The idea of iterative filtering is sort of interesting. So the idea is that you take, at a given particular value of the parameter theta, what you do is that you make up a model, a Bayesian model. And that Bayesian model will take a prior, and your prior is centered at this particular value of theta that you have. Okay, so I take a Gaussian with mean theta with a small variance sigma square. And then given a particular value of from this Gaussian distribution, I look at a random variable y with conditional distribution given by my likelihood function. Okay? So it's a completely made up model, Bayesian model, and I take it and I look at the posterior distribution of it. Of course, as we know, typically when we do Bayesian analysis and we look at posterior distribution, it's always sort of a mix of what's coming from the prior and what's coming from the likelihood function. So since I'm localizing myself in a prior at theta, and the likelihood function is saying that the maximizer, say is this way, if I look at the posterior will be tilted a little bit towards the maximum likelihood, the maximizer of the likelihood function. And if I can sample from that posterior distribution, knowing where I'm starting from, actually I can use that to gain information about the gradient at theta. It turns out that it works exactly like that. That if you look at this posterior distribution, and you take the mean of it, this particular mean would be somewhere between theta and the maximizer of your likelihood function. And you can show precisely that, in fact, the mean, this posterior mean, once you subtract the prior mean from it, the information you get right away, the next term that comes out is actually the gradient at theta, a scale with the variance of the prior that you use. The capital power is the posterior mean that you make up, that you just made up. Yes.
Are you assuming that things are unimodal?
Yes. So we're assuming that not unimodal actually. What we assume in this result is that we have derivatives that are bounded essentially. That your log likelihood is moved to the third order, and you could bound the derivative. So even if you have a situation where, because I'm not saying really anything about the maximizer of here, all I'm saying is that at theta, if I look at this made-up posterior distribution, and I take the mean of it and I compare it to the prior mean, I get the second term is the gradient at theta. It's the gradient of the log likelihood at theta. So your log likelihood function could be multimodal, but if it is smooth at a particular theta, you could get what is the gradient at theta from this result. And then, of course, if it is multimodal, that gradient might lead you to a local mode. Does that answer the question? Okay. So again, the idea is that you could estimate the gradient of your log likelihood function by comparing this made-up posterior mean with the prior mean, and you do the expansion of if you do the expansion of the posterior mean, the first term that comes out actually is the prior mean followed by the the gradient at theta. What that means is that now we have a way of estimating the gradient at any particular point theta, and by just taking this made-up posterior mean, subtract the prior mean, and divide by sigma square, and the term that follows here is all the sigma. This thing is actually O of 1, and it was later on improved actually, and Pierre Jacob and Arnaud Doucet, they looked at it and they improved this term. They showed that it's actually O of sigma to the 4th. So it tells you that if you subtract from this posterior mean the prior mean, you divide by the sigma square, you get the gradient. You get the gradient, and you could actually then use that to do a stochastic approximation, which is exactly what the next slide is about. So we have again to repeat myself. So we made up this posterior distribution. We take its mean. So we have this posterior mean, and we show that in fact it's related to the gradient of the likelihood function. So when the sigma is small, we can approximate the gradient by computing this term. Of course, now because this is a posterior mean, we could approximate it by simulation, and that actually is where we sort of go back to the original problem that even if we cannot actually simulate we cannot actually calculate the density of the observation process, we cannot, and if we can simulate from it, we could get an estimate of this term. So to illustrate that, so let's look at again here a standard latent variable model, which it's sort of the baby version of the state space model, where here this is my latent variable and this is the observation model. So the likelihood is this thing here. So now my made-up model here in this particular case becomes the following. At a particular theta, I draw a new parameter theta, which is normal at theta, at little theta with variance sigma square. Given theta, I draw the signal from this distribution. I guess this should be var theta. Given var theta and small x, I draw the observation. And what we discussed earlier says that essentially that the posterior mean of the parameter in this model, this posterior mean, subtract theta from it and scale by sigma -2, actually gives you an estimate of the log likelihood at theta. So now we have a way of doing stochastic approximation, and we could get this essentially by importance sampling. We could just estimate this term by importance sampling. And then we, at a particular theta, construct an estimate of that thing, use it to move to the next theta. And that's what this slide is about. So the one iteration of the process will be. Let me maybe just present this slide. So one iteration of the process is that the particular iteration, I have theta k. Using theta k, I draw multiple samples from this Gaussian distribution at mean theta k. I draw my signal. I compute the weight as in standard importance sampling. And this is the estimate that I presented in the lemma. That gives me a copy, an approximation of the gradient. I plug it back here in this stochastic gradient step. So you see, the only thing that we really need here is just sample from the signal given the observation. It's a little bit like you could also think of it a little bit like some sort of calibration, essentially, right? Because it's in a way what I'm doing is that I'm sort of drawing copies of the parameter, and then use these to draw the signal, and then compare whether the signal that I draw fit the data, and the fit is used to weight each one of the sample that I draw and I use that essentially to get information on what is the gradient to move. Of course, you could then this, you could rewrite it by saying that this, the theta k plus 1 is theta k plus the gradient plus the error terms, and we have two error terms, the approximation of the gradient, and then the lemma that I presented earlier, the fact that this term is actually approximating the exact gradient. And then you could use, here we use some sort of standard kind of boundary space stochastic approximation ideas to describe a little bit what could be the behavior of the theta k. There are many kind of, the behavior will depend a lot on the function L, obviously. For example, in a very simple case, if you're dealing with a log likelihood that is, say, strongly concave, you could actually get, much simpler, much nicer result for these kind of schemes. So here what we say essentially is that if you have something like that, it will give you, it will converge to stationary point of the gradient of L. Okay. But any questions? One of the issues actually with this method that we from the very beginning we didn't like too much is the fact that we actually divide in two quantities that really are going down to zero, right? So, but of course the numerator is on much smaller scale that I will show, but still both of them are going to zero, and then it could become unstable, particularly as you approach the solution. It turns out that the algorithm later on, by sort of reading a little bit more, we learn about proximal method. And this is actually also very related to the proximal algorithm. That connection can be used to prove a lot more interesting result about the method. So here is the connection. So let me go back again to the middle Bayesian model that we have. So what we're doing is that at a given value of the parameter, we construct this Bayesian model. And we look at the posterior distribution. Of course, the posterior distribution can be written this way, right? And we take the mean of this posterior distribution. But of course, the mean and the mode are two things that are very close oftentimes, provided that, of course, you need to be, at least for a certain class of distribution, the mean and the mode are very close. And the mode of this distribution is the proximal operator of L. So I will use the notation here, prox, to denote the proximal. The function negative L here at theta, which is this quantity here. Essentially, you could think of it as I like to think more about not the arg mean, but the mean itself. If you look at the mean itself, not the arg mean, the mean has a much more nicer interpretation. The mean of that function is kind of an approximation. It's a nice approximation of the function negative L itself. And you could then think of this proximal as a way of trying to do gradient method on this mean. So it turns out that when you look now very closely, what we realized next was that in fact this map posterior mean that we were using is actually much more closer to this proximal operator than to this idea of trying to recover the gradient from it. If you're trying to you look close, you will see, I mean, as I will show next, is actually much closer to this than to the term that I presented earlier in the previous expansion. But just a couple of words on the proximal. Again, looking at this object, and you could show that this thing is non-empty, and if the function is concave, it is uniquely defined. If you take the derivative of that to of this optimization problem, you take the derivative and you set the derivative to 0. It shows that, in fact, if theta k plus 1 is this proximal, is this quantity here, in fact, you have this. And there is another name for this. It's iterating the proximal is actually doing an implicit gradient iteration. The usual gradient would be that I use theta k here instead of theta k plus 1. So this is it. And if the function is strongly concave, this is actually contraction, and you could show a very nice convergence property for it. If it is a proper concave, I mean, this is, in my case here, is proper. If it is concave, if you have the sigma is actually summable, then this actually converges to the minimizer of L. So there is a very, very nice theory This is, I mean, this is well known. There's a lot of work, very well understood way of approximating solution of minimizing the function negative L here. And what we've shown is that, in fact, this posterior mean that I defined earlier is actually directly related to the prox at theta. You have this approximation, and the term that comes in terms of the sigma, it turns out to be really the same. But then there is another term that modulates the remainder here, which actually goes to 0 as you iterate and try to approach the stationary point. And that suggests that, in fact, the approximation gets better than the previous interpretation that we had of the method, and which is, of course, which is what I'm writing here. And using this, we could we get another algorithm basically, which is now that instead of trying to use the Monte Carlo approximation of this and subtract this, rescale to get the gradient, we just take the Monte Carlo approximation of this and just iterate that automatically without trying to get the gradient, and it gives you a slightly different algorithm that actually behaves better. That's what I'm describing here. So here, given theta k, you draw from the parameter, you draw from your observations process, you get the weight, and sorry, this is not right. So I just copy the. There's no sigma in front. There's no theta in the back. I just copied from the previous slide. So this is directly just taking the sum of the Wj theta j here as my g, and then I use that as the next iteration. And of course, now you could write it as the prox and the gap between the g and the mean, and the gap between the mean and the prox. The lemma that I presented earlier gives us some control of this term. The Monte Carlo is understanding the Monte Carlo gives us a control of this term, and we could sort of put these two things together to look at the behavior of these iterations. But we haven't really done much on this, other than the very simple case where we assume that the function L is strongly concave. But if it is say concave only, or even non-concave, what can be said and what is the behavior of this. These are actually technical problems that we haven't sort of really get our hands on. So there's still a lot of things that we could prove about this, and whether we could really rigorously say that this scheme probably say that this scheme actually performs better than the other one is also another question that we're very interested in, because in the simulation we see it in the simulation the difference between the two. One can actually push the idea even further, which is that, again, let me present it in the context of the simple log likelihood function that we have here, L. And let me call here a case of sigma to z, just to denote the Gaussian density, we mean z. Okay? And given a density, or given a function L1 here, f, I will convolve that with the kernel k, k sigma, and I call that c sub sigma f. So this is just, draw a Gaussian with mean 0 and variance sigma square, draw another random variable independently from f, and take the sum of the two. And that's what the distribution of that is what I'm calling c sub sigma f here. Of course, I can extend that to measures by this way. And then let me bring in also the base map, which is that I take a density, for all practical purpose here, and then just weight that with my likelihood and reweight, and let me call that BF. So this is the Bayesian map where the prior is F. And then I'll compose these two maps. So given my prior measure mu, I convolve it with the Gaussian kernel by adding a little bit of noise to it, and get that as a distribution, and use that distribution as a prior, and get a posterior distribution out of it that I'm calling T sub sigma. If I choose this distribution, this measure nu to be the point mass at a particular point theta, so delta here, and I plug the Dirac measure delta theta into this C sigma map here, of course that just gives me a Gaussian density with mean theta, and I use that through my likelihood function through the base map. So this will be exactly the distribution that I call P sub theta sigma earlier. This is exactly the same distribution. But now I'm just allowing myself to consider my prior to be, instead of being the point mass, it could be any probability measure. And another idea is that why not just simply iterate T sigma? Just iterate it. So T sigma, you start from some prior, you add some noise to it, you use it at a prior to get a posterior. That posterior, you bring it back, you add a little bit of prior, you use it at a prior through the likelihood function, and you get in another posterior, you use that posterior again, and you continue doing that without taking any mean. And you do that for, say, n iteration before taking the mean. It turns out that it actually works even better than the other two procedures that we have earlier. And we call that iterating filtering 2. And it's related to this thing that these people call data cloning. And what they do is essentially, for example, if I just omit this this convolution term here, and I'm just iterating my Bayesian map. So starting from F, I look at this, and I use this result as F, and do it again, and bring it back again as F. Of course, that means that after n iteration, or after k iteration, I get my posterior to be something like this. This actually, you can show that this is like some sort of simulated annealing, actually, and it's actually converged as the k increases. It actually converges to a point mass at the MLE, and it was explored in this paper, in this JASA paper, and they call it data cloning. Well, we actually just adding this noise operator that we sort of stick in the middle, and it gives you a lot more in terms of computation, and it behaves a lot better. And we call it iterative filtering 2. And we have some results, but the result is not very, very satisfactory. The only thing that we can prove really nicely is that if you fix the sigma is small, and you take this map T sigma, and you iterate it 1 over sigma times, starting from F. And if you call this, I call theta the random variable that has this distribution. Here I'm assuming that my function is nicely concave. It has a single maximum, and you could show that this actually is O of sigma. But what we really want to say is that for any n after these times, you have that, but it's a little bit complicated. We really don't know how to do it very well. But I really think that this is true. It's probably true that after this many number of iterations, the result that you get really just stays within sigma of the theta hat. But the proof is unclear as how to do it. Briefly, some illustration. Here we have a very simple linear, Gaussian linear state space. Everything is Gaussian. We can compute the answer, and we want to just use that to compare the two iterative filtering. And we simulate we do many simulation of the many run or many paths of the algorithm, and we look at the likelihood that we get after 25 iterations using 1,000 particles to do the sequential Monte Carlo. And after 25 iterations, we look at the solution that we get, and we repeat that 200 times. And we use those 200 values, 200 likelihood values to look at the histogram or the density of what you get after 25 iterations, of comparing the proximal version of the original iterative filtering. And we see that there is actually it's a lot more robust than the iterative filtering one. We also compare iterative filtering 1 and iterative filtering 2, and we also do the comparison with particle MCMC. Particle MCMC turns out to be the Bayesian analog of iterative filtering, in the sense that in PMCMC you want to do, again, Bayesian inference in this state space model where, even in a particular case where the transition density is intractable, PMCMC turns out to be really the analog of what we're doing here. And we did a comparison also with just to illustrate. And there's a package that's the pump package that was developed by Ed and Aaron King and some of the students that worked with them. So here we take a very simple toy example where the signal is constant actually, but we don't, but we still do the sequential Monte Carlo as if it was not. And the observation signal here is just Gaussian noise here. And this picture is what you get after I think it's I'm not sure, I think it's 20 or 25 iteration of each one of these algorithms, but you repeat them 30 times to see the end point that you get after these many iterations. And A is iterative filtering 1, B is iterative filtering 2. and C is PMCMC. Again, you could see that just iterating the map, and after 25 iterations before taking the mean of the particles that you get, actually, it gave you something that is a little bit more, at least on this example, which is better than the original idea of iterative filtering. So that's essentially the talk. It's an idea that we think it's interesting. There's still a lot of ways possible to actually improve it. For example, bringing in gradient information, second order derivative to scale the gradient a little bit better is also another thing that could be done. And the theory is also, there's still a lot that we think remains to be done understanding the way it behaves. And it has been used in really large examples in this Nature paper. And I'll stop here. Thank you.
This is a quick question. Just for long time. There's a break schedule now. We have some discussion. Any quick question? Or?